Welcome back to the You Can Do TV channel.
At Sulfur Point, the port of Tanga, massive custom steel beams are shaped and welded into a structure that will eventually stretch 300 meters, with a span of nearly 70 meters. Each beam is carefully measured and aligned before welding, ensuring the integrity of the final shed. You can almost feel the scale. The steel seems to demand respect before it even leaves the shop. Operators adjust welding parameters and monitor heat distribution across each joint, combining human oversight with automated tracking systems. NNN. Steel plates are cut and drilled using CNC-controlled machinery, allowing intricate connections and support brackets to be fabricated with consistent accuracy. As beams are welded together, temporary supports maintain alignment, preventing any shift under the weight of the steel. That span is wider than some streets. You'd never guess it starts as flat plates and small components. After welding, beams are lifted using heavy-duty cranes, arranged for final assembly at Sulfur Point, and carefully secured to avoid stress points. The structure will serve port operations, supporting cargo handling and storage efficiently. Operators check bolt tension, weld quality, and alignment once more before the beams are transported to their final position. It's wild to see sections so heavy being maneuvered with such control, almost like they're floating. This combination of engineering, careful monitoring, and machine-assisted fabrication makes the shed a reliable backbone for the port. The coordination between teams, cranes, and jigs keeps everything moving smoothly. You can't help but respect the strength packed into each beam. The way they handle such enormous weight is pure engineering muscle. The temporary setups and fine adjustments highlight the balance between machine precision and human judgment, making every meter of the shed count. Rigid steel yields easily under the Himalaya machine's gentle yet firm rollers. Operators guide each metal beam into the machine, adjusting rollers and clamps to match the desired radius. That first bend always catches attention. Metal doesn't fold this cleanly on its own. The machine employs multiple synchronized rollers, pressing and rotating the steel gradually. Hydraulic cylinders drive the bending pressure, allowing fine control over speed and curvature. It's easy to forget how much coordination goes into a smooth bend. This setup almost feels alive. Adjustable stops ensure every section matches exact specifications.
Steel trusses spanning up to 300 feet wide are produced at Brightspan's facility in Canada, each one engineered for strength and verified step by step. The video shows how steel tubes, plates, and fittings become full structural systems, each one verified, assembled, and finished under tight inspection. Every blueprint guides the production team like a roadmap, leaving little room for error. Steel tubes first enter the CNC-controlled bending machine, where operators program exact measurements using the VemPro system. The tubes, up to 170 inches long, are shaped and then clipped at both ends for welding. Production orders include every part number and blueprint, ensuring that material selection and dimensions stay consistent. Each operator double-checks measurements before the next step begins. The organization here is no joke. Everything moves like clockwork. Next, tubes move to the cold saw and drill press, which handle diameters up to 4.5 inches and lengths reaching 48 feet. Templates guide the drill press to guarantee that holes align across repeated parts. The precision in drilling ensures all trusses fit perfectly in the field. Welders then assemble subcomponents in large welding cells, some supported by 3-ton and 5-ton cranes for the biggest trusses. The teamwork between machines and welders really stands out in this phase. The Davi roller shapes pipes to precise radii, verified against gauges before further assembly. Materials from approved suppliers undergo receiving inspection, confirming all dimensions match the drawings. Minor adjustments are made if measurements are slightly off, ensuring quality compliance. Once everything checks out, technicians weld, clean, and prepare assemblies for the next stage. The robotic welding cells handle repetitive jobs, tacking and completing welds while operators inspect for any variance. Trusses are cleaned, bundled, and labeled with part numbers for traceability. Each robot is programmed to follow a specific weld path, reducing human error. You'd almost think each weld has its own identity card here. Quality checks never stop. Each subcomponent is verified against engineering drawings, and all welders follow standardized weld procedures. The Whitney plasma punch processes 5 by 10 foot steel sheets up to half an inch thick, cutting and punching with numerical precision. Operators confirm that the right dies are installed before starting each program. Purlin production uses hydraulic presses and ironworkers to flatten, punch, and form supports for trusses. Each purlin is made from either pre-galvanized or hot-dip steel, depending on its structural role. Small parts go through a parts cleaner to remove burrs and debris before final assembly. Cleaning ensures no debris will interfere with the final weld or assembly. Finally, fully welded trusses are sent for hot dip galvanizing, a defining stage ensuring corrosion resistance. After cleaning and zinc dipping, every piece is rechecked, smoothed, bundled, and certified before shipment. Finished trusses are staged carefully to prevent damage during transport. Seeing every truss tagged and approved gives the sense that nothing leaves unfinished. Towering piles of crushed stone hint at the scale of operations at White's Creek Quarry, where each phase transforms raw rock into products that build communities. Phase 1 begins with precise drilling and blasting. Holes are drilled in a planned pattern, loaded with explosives, and detonated milliseconds apart to reduce vibration. The timing control on these blasts is surprisingly clever, like orchestrating a stone symphony. Phase 2 moves the material from the muck pile to the primary crusher. Two 60-ton haul trucks, loaded by either a Cat 9 88F front-end loader or a Volvo 460 track loader, transport rock 500 feet, to the primary crusher. Seeing those trucks rumble through is oddly satisfying in its own way. Crushing and screening in Phase 3 transforms rocks of 3 to 12 inches into precisely sized products. A 42 by 48 jaw crusher handles the primary crushing, while a vibrating scalping screen and an AP20 triple deck sizing screen sort material. Oversized rock enters secondary or tertiary crushers, and material between 1 inch and 1/4 inch goes to the wash plant. It's amazing how many steps it takes for the final stone to meet customer specs. Phase 4 loads and tickets customers. Volvo 220 front-end loaders fill 23-ton loads, and trucks receive printed tickets. Safety is paramount. Dust is suppressed with collected rainwater, and employee injuries are minimized. A quarry might look rough, but the organization behind every scoop and truckload is impressive. The variety of products includes 3/4 stone crusher run, 1/2 stone, and riprap for erosion control. Every product here has a clear purpose, and the teamwork to get it there is clear. Feel the impact as each steel pile is hammered into Banda Aceh's riverbed. The process starts with positioning the 500 mm diameter steel piles, guided by the Nisha DH350 crane. Seeing these massive steel columns lined up makes you realize the scale of civil engineering at work. Workers carefully lift each pile with the crane and align it vertically. The hammer driving is executed from a single support point, or E4 position, ensuring stability. Concrete and metal meet the earth, and the hammer strikes repeatedly until the pile begins to penetrate the ground. The rhythm of each strike is oddly satisfying in its own right. You can't help but notice the discipline required. When piles are driven, the next step is welding connections for continuous length. Each joint is fused using electric arc welding, producing strong, seamless connections to withstand structural loads. One pile can literally carry the weight of several floors above. Following pile placement and welding, workers conduct a calendaring test to check for hard soil. Using rulers, millimeter paper, and pencils, they measure penetration over 10 final hammer blows. If the pile moves more than 1 inch, 2.54 centimeters, driving continues. If not, installation is confirmed. Funny how measuring something so large can involve just paper and pencil. This thorough process ensures that each steel pile reaches the depth required, in this case up to 32 meters hard soil, providing stability for the bridge structure. Proper testing guarantees the safety and longevity of the construction. One wouldn't expect such simple tools to validate such heavy engineering work, but it works perfectly. Finally, each pile is checked, adjusted, and verified before moving to the next. The sequence of erection, hammer driving, welding, and calendaring repeats for all P5 pillars of the bridge. The coordination between crane operators, welders, and survey teams is essential. The teamwork here reminds you that civil engineering is as much about people as it is about steel and machines. The efficiency and attention to detail in Banda Aceh's bridge construction are impressive. The process may look repetitive, but every step safeguards the structure. You might even smile watching how the largest piles are tested with just a pencil and millimeter paper. Rising over the Swat River, the Moman Dam's construction involves intricate coordination across multiple sites. Diversion tunnels redirect water, while outlet portals regulate flow to protect the spillway. Workers navigate access tunnels to reach the spillway site and re-regulation pond, with cranes and batching plants supporting concrete work. Both left and right banks host contractor camps, project offices, and WAPDA facilities, all within a 20 kilometers long security perimeter. Trees are planted along the banks and solar panels installed at schools and mosques. The teamwork here is impressive, seeing engineers and crews manage so many areas at once. Even the access rods seem like tiny lifelines for daily operations.
Human hands and bending machines work together to convert straight steel bars into rigid cages for concrete. The first step involves measuring the required lengths using tape measures, ensuring every segment fits perfectly within the beam or pillar design. Next comes cutting. The steel bars are placed firmly on the machine bed before the blade engages. The cutting machine snaps through the steel bars, creating clean edges for assembly, etch and N. After cutting, stirrups are formed using a specialized bending machine, shaped according to the required design. The bending machine allows adjustments from multiple angles and diameters. The machine's horizontal setup ensures bars are bent consistently along the length. It's almost hypnotic how a straight steel bar twists into a precise loop ready for reinforcement. Workers keep their hands steady while feeding bars into the machine.
In modern agriculture and fencing systems, durability starts from the ground up. The production of high-strength concrete posts plays a critical role in supporting raspberry trellises and protective barriers. Production starts with formwork preparation. Molds are cleaned, inspected, and coated with a release agent to ensure smooth demolding. This step ensures that each concrete post maintains dimensional accuracy and a smooth surface finish. Next comes mixing the concrete. A precisely measured mixture of cement, sand, gravel, water, and optional additives is prepared. The composition is tailored to achieve the required strength and durability for long-term outdoor use. Once the mix is ready, the forms are filled. Concrete is poured evenly into each mold, ensuring no air pockets or inconsistencies. Vibration compaction, or vibrosettling, is then applied. The molds are placed on a vibrating table, allowing the concrete to settle densely, removing air and increasing structural integrity. For added strength, reinforcement bars, rebar, are inserted into the center of each form. This reinforcement ensures the post can withstand mechanical loads, wind stress, and the tension from trellised plants. A second round of vibration follows, fully embedding the rebar and consolidating the concrete. After curing time, the posts go through demolding. The finished concrete posts are uniform, robust, and ready for use, ideal for raspberry plantations, fencing systems, or vineyard supports. What makes a prefabricated basement rise in just one day at Vertikeller? Each prefabricated component is engineered to strict specifications and delivered directly to the site, allowing a full basement to be assembled in a single day. It's impressive how a full cellar rises so quickly without cutting corners on quality. The process starts with precision planning in the technical office. Individual designs are translated into exact production data that feed the automated production line in Newmarket, Calham. Wall elements, floor panels, and additional features like balconies or bay windows are manufactured largely automatically under optimal conditions. The automation here really reduces human error, and that's something every builder can appreciate. On-site, ITER installers follow a clear sequence. Foundation slabs with embedded rebar and joint tape form the base. Wall elements are placed room by room, with ceiling panels supported on temporary structures. Stairs, straight or spiral, are positioned and immediately usable for construction. The first time seeing a staircase ready for foot traffic right after assembly is wild. Electricians connect embedded wiring and outlets, while masons oversee additional reinforcement and formwork. Once all preparatory work is complete, filling concrete is poured into hollow walls and ceiling panels, producing smooth, joint-free surfaces ideal for painting. Every pour showcases how planning and prefabrication make construction almost effortless. With CE-certified elements, quick installation, and consistent quality, Vertikeller delivers a cost-effective, reliable, and high-quality basement solution. Honestly, this system makes finishing a basement in one day feel achievable for real. Herbers. Eco Asphalt uses renewable oils for reactive binders, installed with a paver. 240 tons reduce 4.7 tons CO2, adaptable to -10 degrees Celsius. Cold lay efficiency boosts worker safety. This saves serious emissions. Rails need precision and strength to support countless trains, and every millimeter matters. The AMS 200 mobile welding machine from Schlatter brings efficiency and accuracy together, replacing 2 by 12 meters rails while restoring track alignment in a single workflow. The fact that it combines distressing and flash butt welding in one operation really cuts down time and complexity. The machine provides the necessary force to achieve calculated dilatation, accounting for material loss during welding. Its long travel ensures reliable distressing, even in low temperatures. Seeing such controlled force applied along rails is like watching a giant piano being tuned perfectly, somehow mechanical, yet almost artistic. Rail ends are clamped firmly, while the integrated deburring unit removes burrs immediately after welding, independent from the movable side. This step prevents imperfections that could compromise track safety. Free space around the rail foot avoids collisions with sleepers and fasteners, reducing the need for lifting rail ends. The distressing force acts within the rail's neutral zone, which not only improves weld quality but also protects the machine from unnecessary stress. It's cool that a machine this heavy can work precisely without shaking the track itself. AFETY. Super Road Flex, the truck-based system variant, allows mobile operation on both road and rail, maximizing flexibility for repair crews. Rails are replaced and neutralization welding ensures the line remains stable. For engineers, this efficiency means fewer interruptions to train schedules and smoother maintenance planning. The MS200 integrates multiple functions into one compact mobile unit. It almost feels like a Swiss Army knife for rails, deburring, welding, and distressing all in one go. Operators can carry out a full welding sequence without switching devices, which is especially valuable in remote track sections. Replacement rails are installed with exact precision, ensuring long-term reliability and minimal disruption to traffic. You wouldn't expect a truck-mounted machine to handle such fine alignment, but it does. The mobile design, coupled with sophisticated mechanical engineering, exemplifies modern rail maintenance. Safety, speed, and reliability are all enhanced. From long travel for distressing to precise flash welding, the AMS200 keeps tracks safe and trains running smoothly. This is mobile welding redefined for efficiency and track integrity. Few molds can combine elasticity, UV resistance, and precision like Cayman DIZAJN's rubber molds for artificial stone. At Cayman DIZAJN, rubber molds for artificial stone are produced under high temperature and pressure, 160 degrees Celsius and 200 bars, ensuring resilience and precision. Every mold undergoes rigorous temperature and pressure control to maintain consistency. It's wild to think the rubber quality matches tire rubber, yet here it crafts walls and panels instead of roads. The production process begins with carefully formulated silicone latex polyurethane. Each batch of silicone is weighed and mixed according to strict ratios. The material is degassed to remove air, preventing fungi or imperfections on the finished veneer. Molds are poured and allowed to set, sometimes staying in the mold for a couple of days to achieve perfect form. High-pressure degassing ensures no trapped bubbles remain inside the molds. Seeing a single mold maintain its shape for years really hits how reliable these are. Once cured, the molds are flexible yet firm, ready to reproduce consistent textures with high fidelity. Hardness is around 40 shores, wear-resistant and UV-resistant, making them suitable for long-term exterior applications. Color consistency is checked for every mold produced. Spraying water into molds before filling ensures easy release of the concrete mixture. Each mold is made to customer specifications, with designs kept in production so models can be recreated years later if needed. Customer specifications include every contour and surface detail. The elasticity of these molds almost makes you want to bounce them like stress balls. Okay, maybe don't, but you get the idea. Production efficiency is high, allowing orders over 10 square meters to be fulfilled within 15 working days. Molds are carefully packaged on pallets or in cardboard boxes depending on the order size. Packaging ranges from pallets to cardboard boxes depending on quantity, and international customers organize forwarding from Croatia. Each shipment includes a quality checklist to guarantee standards. Quality testing and CE certification guarantee that each mold can be used continuously for at least 5 years without degradation. Black or gray rubber is standard, and pricing is proportional to weight, €12 per kilogram. Something so technical can also feel like an art form when it shapes natural-looking stone. The workflow combines chemistry, engineering, and craft. Mixing, degassing, molding, curing, and final testing. Maintenance instructions are included to extend mold lifespan. This process produces veneers that are precise, elastic, and durable, ideal for wall paneling, cladding, and decorative surfaces. Each mold's flexibility allows fine details to be captured repeatedly without wear, ensuring authentic-looking stone surfaces. Final inspections ensure no mold leaves the factory with defects. The combination of material science, customer customization, and production discipline makes Moman Dam molds stand out in the industry. Honestly, seeing the molds hold up for 5 years straight is a reminder that good engineering can really last.
In the specialized process of glass handling, precision and safety are essential at every step. The operation begins as a custom-designed glass transport truck slowly reverses into the designated unloading zone. This specialized vehicle is equipped with a hydraulic suspension system that allows the entire chassis to lower close to ground level, minimizing the drop height and enabling smooth, controlled unloading of fragile glass panels. Once positioned, a vacuum lifting machine, specifically designed for glass, carefully attaches to the surface of panel. With calibrated suction and steady motion, the device lifts and transfers the sheets into storage. Each panel is separated by protective pads and safety spacers, placed meticulously to prevent breakage, surface scratches, or internal stress. Operators use protective gear and follow strict handling protocols to ensure both personnel safety and material integrity. The panels are then stacked in vertical racks or custom shelves inside the warehouse, ready for further processing or delivery. This entire operation reflects the precision, care, and advanced engineering behind modern glass logistics, delivering fragile materials safely and flawlessly every time.
How does ordinary raw material become flawless flat glass ready for your windows? In the batch house, technicians measure and mix ingredients precisely, incorporating recycled cullet, broken glass returned by customers, to reduce raw material consumption. It's clever how old glass gets a second life without compromising quality. The blended batch moves into a 36-foot wide furnace, heated up to 3,000 degrees Fahrenheit. A charger pushes the materials into the molten pool, forming a 4-foot deep body of liquid glass. The molten glass then glides across the tin bath, spreading into a broad ribbon with uniform thickness. Skilled operators adjust the configuration in real time, maintaining exact tolerances. Who knew a tin bath could serve as both conveyor and sculptor? After leaving the tin, the ribbon passes through the annealing layer, cooling slowly to release internal stress and ensure uniformity. At the cold end, 20 miles of glass ribbon are cut, edge-trimmed, and defect-checked using lasers, cameras, and special lighting. The bump roll snapping the glass along scored lines almost looks like magic. Finally, the glass panes are routed to the packing station, where orientation, wrapping, and labeling are carefully managed for delivery. Even in such large-scale production, every pane seems to get personal attention. This workflow highlights how heat, mechanics, and human oversight converge to produce over 600 tons of high-quality glass every day. Some of these panes look so perfect, it feels like they've been polished twice, once by fire, once by hands. N.
Bright orange copper ingots line up in SMS Group's non-ferrous metals plant, each one a step toward becoming the raw material that powers industries worldwide. See how copper is melted, cast, cooled, and processed into sheets, rods, and coils? Copper scrap or concentrate is first charged into electric furnaces. High currents heat the metal until it reaches its molten state, while operators monitor temperature and chemical composition. Once molten, the copper is cast into large ingots or slabs and cooled on casting beds. These solid blocks are later sent to rolling mills. At the rolling mills, ingots are reheated and pressed into sheets or rods of specific dimensions. Hydraulic presses and rollers shape the metal, while inline gauges ensure the thickness and width meet strict tolerances. Coils are then annealed in furnaces to soften the metal and relieve internal stresses, producing material ready for industrial applications. NNN. Throughout the plant, quality checks ensure purity, weight, and size compliance. It's easy to forget how essential these processes are to electrical wiring, plumbing, and countless other products. Copper coils and sheets are bundled, labeled, and prepared for shipment, completing the cycle from raw metal to finished industrial products. NNN. Aluminum tubes are thin, but still form robust frames for professional bicycles. In the Foshan Metal Alloy Science and Tech Company, Limited, aluminum sheets are transformed into bicycle frames designed for strength, lightness, and durability. The production line begins by cutting aluminum tubes to precise lengths, each piece verified for uniformity. In. It's surprising how such thin metal can become the backbone of a bike that supports both speed and weight. CNC machines drill and shape the tubes, creating exact points for joints and brackets, ensuring each frame will be structurally sound. N1. Next, welding robots and skilled operators join the frame components. Heat control is closely monitored to prevent warping, while jigs hold pieces in exact alignment. After welding, frames undergo grinding and polishing to smooth the joints and prepare surfaces for coatings. Quality control checks include measuring frame geometry, verifying weld strength, and inspecting the surface finish. It's neat seeing how industrial machinery and human oversight collaborate to produce hundreds of frames with consistent quality. Finally, each frame is tested for rigidity and alignment before being packaged for shipment, ensuring cyclists will receive a reliable, lightweight structure ready for the road. Aluminum may not have the prestige of titanium or carbon fiber, but these frames prove efficiency, affordability, and reliability can ride together. 5 axes move in harmony at Heller Lapia, shaping steel into a microscope housing that fits microscopic tolerances. Operators set up the steel blank on the PCU-100 machining unit, securing it with high-strength clamps that prevent any movement during the multi-axis process. The machine alternates between milling and turning, approaching the component from all directions. It's impressive how the same tool can reach hidden pockets without repositioning the part manually. And C. CAM programming defines every movement. Spindle speeds and feed rates are adjusted to match the steel grade, balancing cutting force and surface finish. Coolant channels remove chips and reduce heat, preventing warping of the delicate structure. Watching the spindle glide around tight curves and deep cavities almost feels like watching a sculptor at work. Once the roughing cycles are done, fine finishing cuts refine all surfaces and critical threads. The 5-axis kinematics allows undercuts and complex geometries that would otherwise require multiple setups. That precision guarantees each microscope housing meets stringent optical assembly tolerances. Finished parts are removed, inspected, and prepared for further assembly. Can't believe such compact steel becomes the backbone of a high-precision instrument. The CP6000 demonstrates how high-speed multi-axis machining can handle tiny, intricate components with full control. You could almost mistake the operation for a robotic dance, every move calculated and smooth. The combination of milling and turning in a single clamping reduces time, maintains accuracy, and minimizes human error, making it ideal for scientific-grade instruments. Super bearings. Production line creates high-strength bearings designed for industrial and automotive use. Forged blanks enter the workflow heated in automatic electric induction furnaces to reach exact metallurgical conditions. The glow of the metal signals the start of a complex journey. Steam rises gently from the furnaces, hinting at the hidden transformations inside. It's fascinating to see raw metal prepared to withstand high speeds and extreme loads. Once at proper temperature, the blanks move to forging presses, shaping them into preliminary bearing forms. Each press stroke adds strength to the core of the bearing. You can almost feel the force needed to bend solid metal like this. Heat treatment follows, including salt bath tempering, which hardens the metal while preserving ductility. Temperatures are logged continuously to guarantee uniform results. Skilled operators closely monitor temperatures and timings, ensuring consistency across batches. CNC turning and grinding machines refine the dimensions to tight tolerances. The interplay of cutting tools and rotation produces surfaces ready for high-speed operation. Even the tiniest adjustment here changes the whole performance of the bearing. It's almost wild that the final diameter is accurate down to microns after all these heavy-duty operations and laser marking machines engrave each bearing with identification codes, guaranteeing traceability and authenticity. Each code is like a fingerprint, unique to its bearing. Every bearing has its own story, quietly waiting to serve in machines around the world. Next, bearings are assembled on automated lines. Rollers, cages, and races are fitted, with every shoulder distance manually checked for conformity. Operators adjust alignment if any misfit is detected. Hydraulic presses ensure oil seals are correctly seated, while automatic grease filling machines prepare each unit for optimal lubrication. And grease quantities are monitored for consistency. Testing equipment from Toyo, Japan measures dimensional accuracy and verifies rotation smoothness under operational loads. Sensors record torque and rotation resistance values for each batch. This part always makes you respect the patience and skill behind bearing production. GATNNN. After assembly, bearings are cleaned, oiled, and packaged. Packaging lines sort bearings by size and type. Operators conduct final inspections, confirming that every component meets Supra's high standards. The combination of automated precision and human vigilance ensures each bearing will perform reliably, whether in industrial machinery, vehicles, or other critical applications. Super bearings. Process balances efficiency with thorough quality control, turning metal into components capable of enduring intense mechanical stress. Every step, from induction heating to final packaging, contributes to a product that engineers and end users can trust. It's neat how high-tech machines and human oversight work hand in hand to produce thousands of bearings with identical specifications.
With up to 52 kilowatts of drive power and 6,750 Newton meters of torque, the CTX Delta 6000 TC is made for the toughest machining demands. This machine serves industries from aerospace to transportation, where both strength and exactness matter in every detail. Its scale and performance already feel like something from the future. Each operation begins with the main and counter spindles, both capable of handling up to 52 kilowatts of drive power and delivering a massive 6,750 Newton meters of torque. They rotate components with stability that ensures accuracy across large diameters up to 510 millimeters. You could almost call this machine a sculptor for steel. That N. The spindle speed reaches 1,000 revolutions per minute, while the milling spindle, equipped with HSK 100A or Capto C8 tooling, runs at 12,000 revolutions per minute for high-speed cutting. Automatic tool changes are handled through a chain magazine that holds 50 tools, expandable to 180, each up to 600 millimeters long and 30 kilograms in weight N. A tailstock with 150 mm quill stroke and up to 3 steady rests provide firm support for long workpieces, maintaining rigidity through complex turning and milling tasks. Every detail of the CTX Delta 6000 TC emphasizes control, balance, and reliability. Quality is critical in producing turbine shafts, transmission parts, and other high-value components. You can almost imagine this machine building jet engines all day without breaking stride. Its engineering proves why DMG Mirai remains one of the leaders in hybrid machining systems worldwide. The sight of a blade gliding through solid aluminum at that speed feels unreal. Yet the Surma's 013110 does it effortlessly. The blade moves through a 12-inch billet in just 11 seconds, cutting with an in-feed speed of 1.8 inches per second. The entire motion is smooth yet forceful, showing how industrial power can stay controlled. You almost expect sparks, but it's the clean cut that steals attention. Each billet enters automatically through a full line. Manipulators position it, marking and measuring systems verify data, and stacking units take over once the cut is done. The system keeps chips to a minimum thanks to a reduced kerf width, meaning less waste and lower cost. Surface roughness stays between raw 5 and 10 micrometers, delivering clean results straight from the saw. Hard to imagine that level of finish coming directly off such a fast blade. Automation handles most of the process, while operators supervise from control panels. That mix of human oversight and mechanical precision defines efficiency here. Surmas, drawing on 5 decades of sawing innovation, continues refining its billet saws for aluminum and non-ferrous materials. You'd think the machine would roar, but instead it hums like confidence itself. It takes intense pressure to make a grinding media ball that survives thousands of crushing impacts. Pipelines built for Nord Stream must endure high pressure deep below the Baltic Sea. Each pipe is produced under strict supervision, with steel plates tested for density and coating adherence. Handling multi-ton steel webs. The HAWART Stegsetzer positions each one with a consistency measured in millimeters. This system is designed to lift, align, and fix heavy steel webs between girder flanges during bridge beam fabrication. One wrong alignment here could throw off the entire structure, so this step really carries weight, literally. The lift-up frame raises the web plates smoothly, guided by hydraulic control. Once in place, positioning units secure the plate with repetitive accuracy, holding it steady while robotic welding follows. It's wild how calm the movement looks for something handling tons of steel. Afterward, the secured lattice structure maintains torsion-free balance, ensuring the beam's long-term stability during load tests. When production demands both power and repeatable precision, the Stegsetzer's robust design delivers. Operators can depend on its secure transport mechanism to move massive parts without distortion. Machines like this quietly decide whether bridges stand straight for decades. Each stage at Toyota's Motomachi plant reveals the careful integration of the Mirai's chassis and fuel cell system. The facility, once known for building the LFA supercar, now focuses on producing the Mirai, a hydrogen-powered sedan that represents Toyota's commitment to a cleaner future. Each movement in this line feels like a quiet statement of progress. And now, the process begins as the CFRP, carbon fiber reinforced plastic, stack frame takes its place at the assembly area. This lightweight yet incredibly strong structure supports the core components of the Mirai's hydrogen system. Workers align it with exact positioning tools to ensure every bolt connects seamlessly. You can sense how every part seems designed to fit with absolute purpose. Once the frame is secured, the fuel cell stack, the heart of the Mirai, is positioned and installed. It's here that hydrogen and oxygen will later generate electricity to power the car. Following this, technicians attach the boost converter, hydrogen tank, and intricate tube network. That web of silver lines almost looks like veins carrying life into the machine. A helium-based hydrogen leak test then confirms the system's airtight integrity, ensuring no gas escapes. The attention to safety is unmistakable. After validation, the fuel cell stack and hydrogen tank are mounted simultaneously, streamlining assembly and balancing the vehicle's layout. This synchronized installation shows how planning meets practical design. Next, the electric motor is prepared, followed by the marriage of the air compressor to the stack, a critical pairing that supplies air for the electrochemical reaction. Then come the drive shaft, front axle, inverter, water heating unit, and high-voltage cables. It's wild to see how many systems intertwine in such limited space. Finally, the front suspension, rear axle, bumper, and wheels complete the chassis build. By the end, what began as a bare structure now stands as a nearly complete hydrogen vehicle ready for final testing. The quiet power behind this process feels futuristic, yet grounded in craftsmanship. You can see every step of copper becoming cable through heat, motion, and precision extrusion. Thick copper rods move through the Sanhang cable plant, stripped and drawn into precise strands. To prepare them for insulation, each strand is annealed for flexibility and strength. Polyvinyl chloride is then melted and extruded around the conductors to form a uniform coating. The smoothness of that coating decides how long the cable will last under stress. Cooling water solidifies the PVC instantly, locking it in place. Operators coil the finished lines onto reels, checking diameter and resistance before packing. There's something oddly satisfying about seeing copper vanish under the white layer. Each reel carries the effort of accuracy and consistency, essential for power systems worldwide.